Okay, welcome back everybody. We're going to run through a bunch of stuff in this lecture, and I'm going to go into more details in the follow-up lectures. So the next two scheduled classes, Friday and Monday, I'm going to prepare videos for you. So I'll probably put them up tonight. You can read through them. Again, I'll be giving you a midterm as well. We're going to be doing our midterm probably through here. Minimal sufficient stats that I'll begin today, and I'll provide a supplementary lecture. I'll also be talking about these two things in the supplementary lecture. So maybe read up on ancillary stats too. I might give you a midterm question on that. I don't feel incredibly guilty because you're going to have a week to do the midterm, and it's take home, and you've got all of your resources. The only resources that you don't get for the midterm is collaboration. And so do it yourself. I really hope everybody gets a 100%. So it should be designed to do that, minus little token errors that we all make. So definitely do your best work. It's meant to get you to study and to really reinforce all of this stuff. So take the opportunity. We're going to go through the factorization theorem today. That concerns how sufficient statistics factorize out. And so if you remember that definition of a sufficient statistic, where if we have the original data set and it's conditioned on the sufficient statistic, that distribution doesn't depend on a parameter. And that's because we take the ratio of two different distributions and things are canceling out of the ratio. I like to think of that as those two distributions and that ratio that we've been talking about, and I'll write it down again. If things are canceling, then it's because they're factorizing out. And so that's almost obvious that that's true, that things do have to factorize out. And that's how I even recognize sufficient statistics, is through the factorization theorem. And so our definition of sufficient statistics kind of requires us to know what the sufficient stat is, and then we can verify it. And we have a tool for doing that. The factorization theorem will give us a tool for recognizing the sufficient stats. We're going to start out with minimal sufficiency. I'll at least allude to it today, what it is, but it's basically the smallest dimensional statistic that you can have that has all the information about the parameter space. So one sufficient statistic, and it's always true, is the original data set. So that's always sufficient. So the data you collect is sufficient for inferring theta, so long as you have enough data. So you might have an example like you only see one data point and I ask you to infer the variance and the mean in the normal model. Good luck getting a variance estimate on that. Even though x1 is the sufficient statistic, if you only have one data point, you're not going to do very well in that inference, nor should you. So you have no real notion of variability with one data point. And so even though that would be the sufficient statistic in that case, it's not enough information to infer everything. So what we want to think about is how to compress these sufficient statistics down and retain all of the information in the original data set. Ancillary statistics are kind of the opposite thing. And they're the statistics that don't have any information about the parameter set. And so when Fisher was thinking about these two notions, sufficiency and ancillarity, he thought that they had to live in non-overlapping spaces. And that's not true. So you would think that they have to be somehow separated. One part of the space has information about theta, one part does not have information about theta. What Fisher came to conclude is that there's another notion that we need to include so that these two things do live in different spaces. And that's the notion of completeness. We're not going to go into that in any great detail in this class. I gave you one homework problem. It's hard if you didn't have the solution manual. And so verifying things are complete stats is difficult. But from a mathematical standpoint, it's interesting. But I've never in practice said, hey, I've got this minimal sufficient statistic, and nobody's ever come up to me and said, oh, is it complete? And is it living in a different space than all other ancillary statistics? We don't do that because who cares? But from a technical mathematical perspective, that's fascinating. So I will tell you in the follow-up lectures what a complete stat is. but we're not going to study it in great detail. I just want you to know what it is, so that if somebody comes up with it, you're not baffled by what they said. There's a theorem relating to all three of these things called Basu's theorem, and we will not cover it in this class. So, for the reasons I just said. I want more time for you to code up things like the expectation maximization algorithm. So I want to spend our time there on things that you're actually going to use in practice. But if you want to read through Basu's theorem, there are some shortcuts on showing things are minimal sufficient. And if you want to use those techniques on a test, I think Jess had asked, can I use Basu's theorem? So yeah, you can use it. Of course you can. And you'll get full credit for that sort of stuff. It's just not something I'm going to test you on. So Jess wants to know all about it, so she's going to study it and work extra problems pertaining to it because she's interested in that. That's okay. So I'm also interested, but I don't want to spend all of our attention there. Another thing that we're going to cover is the likelihood principle, and it's going to be pretty low key. And when we get into chapter 7, I'll ask you things like, did we violate the likelihood principle? The problem with the likelihood principle in practice is that it doesn't tell you exactly what to do. So I'll just say real quickly what the likelihood principle says. If two likelihoods are proportional to each other, and you have two scientists interested in evaluating or estimating some parameter, inferring it, this is inference class, so they want to do something with that parameter and they want to learn it. So the likelihood principle says if you have two individuals with the same parameter that they're learning, and they both have likelihood functions that are proportional to each other, i.e. they're the same shapes. So if they're proportional to each other, they're just kind of lifted up and down. So same likelihood function, essentially. If the likelihood functions are proportional to each other between two different experimenters, then those experimenters should make the same inferences. And I kind of get that. But it doesn't tell us what we're exactly supposed to do with the likelihood function. And so maybe you're a Bayesian. Maybe you're a maximum likelihoodist. And so there's no dictatorship on what you do with your likelihood and what is the correct thing. So the statement in the likelihood principle is a little bit weak, where it says, or maybe it's too strong. Yeah, let's say it that way. It's too strong of a statement. If likelihoods are proportional to each other, then you should get the same inferences. But it doesn't tell you exactly how to operate on the likelihood function. What I do like about likelihood functions is that they have all the information in the sample, i.e. they're always conditioned on sufficient statistics. And so there's a conditioning there. And that's what's called the conditionality principle. So sufficiency principle and conditionality principle are supposed to add up to the likelihood principle. Birnbaum tried to prove that back in the 60s. It's unfortunate that his proof is slightly flawed. It doesn't require you to do this. Mohammed's going to come in and give you a lecture on the likelihood principle on March 29th. And so I'm going to let him talk about it. So we're going to skip ahead when we get back and jump into chapter 7. And then Mohammed is going to pick up a lecture and he's going to discuss the likelihood principle. I'll come in and I'll talk about it. But I will warn you, this is usually prompts an argument. And so different camps, some people subscribe to this principle and say you have to do it. Some people say you don't have to do it. And then they fight. So business as usual. So anyway, I have a love-hate relationship with the likelihood principle. I think it's a good idea, but you don't have to adhere to it. There's no it's not necessary to adhere to it. There's a lot of ways to do statistics. But I'll just say, March 29th, Mohammed is going to have his first teaching experience here at Virginia Tech, so give him a warm welcome. And then I'll come in and I'll answer some questions about this afterwards. What I really want to do is just ask you, did we violate the likelihood principle when we develop estimators, and do you care? And you might say, I don't care. You might say, actually, I do care. So anyway, you can violate the likelihood principle and come up with the same estimators that you would get if you adhere to the likelihood principle. And so it's really a statement about how you go about business, not what your answers are. So that's kind of interesting and tricky. So I don't like people telling me what I have to do, but I don't mind people looking at my results and evaluating whether or not it was good. So depends on which day it is. Okay, let's come back around right here, Factorization Theorem. This is in your book, so I'm going to cover it. But the Factorization Theorem says, this says that if Tx is sufficient, then the factorization exists. I'll write down what that factorization is. We'll just write this down. It's going to say that my distribution, f of x, x is my sample, given theta, is going to factorize into two components. So it's going to factorize into a component that only involves the data, and then it's going to factorize into another function that only contains the sufficient statistic and the parameter. So if Tx is sufficient, then everything factorizes. And we can kind of intuitively figure that out. The factorization theorem is a little bit stronger as well. If this factorization exists, then Tx is sufficient. So there's this other statement. And if the factorization which factorization? This one. Then Tx is sufficient. So I guess if somebody would have shown me this a long time ago and said that, I'd go, yeah, duh. It has to be. There's a little bit more formality that we have to follow if we're going to be mathematicians about this. We can't just go, well, yeah, obviously. So even though a lot of mathematicians do say that. So they're always like, it's obvious that. Those are the things that they don't feel like proving anymore. So we'll provide a proof for this. So let's just do it. So let's go this direction first. So we'll do this first. I'll put a 1 in there. And then we'll do this second. Okay. And then I kind of like to talk about the second part because there's some interesting stuff. And then again, it's all back to transformation of variables. And so I like you guys to know how to transform random variables, and you can do it in your sleep. I wake you up. And you're like, I'm ready to transform some random variables. So it should be like that immediate for you. You're ready to do it. You're frothing at the mouth to transform random variables. We do it all the time. So anyway, we'll say a few things about it. And we'll go back to kind of our first probability class to understand what a transform is. And that's kind of the ingredient in the proof that we need. So first, this is the easy one. I'm just going to write down Tx is sufficient. That's what we're going to start with. And now we're going to show that the factorization exists. So I can write down Fx given theta is equal to Fx T of x, no extra information, I just am throwing in something that I can calculate. So if I have x and I can calculate that thing, there's no extra randomness. Same thing that we've been doing. So f, now this is f x given tx and theta f tx given theta. And if you showed me this and didn't tell me tx was sufficient, I would say, yeah, that's always true. So that's just the rule that I learned in probability theory that has never not been true since I learned it. So we can always write things down conditionally. So since tx is sufficient, this isn't a function of theta. So this is that ratio again. So what is this thing? This is just f of x given, I'll just write it down this way, f of x given theta divided by f of tx given theta. This is the same thing as that, right up here. So I'll just write it down one more time. That's really f of x and t of x given theta. They're the same things. So it's just the ratio of these two different distributions. And again, the way I think about this is they have the same shapes. And so that's going to be a constant with respect to theta if t of x is sufficient. Okay, so we've just completed this part of the proof. I'll just write this down one more line. This is f of x, t of x, f of t of x given theta. I'm going to call that h of x. It's just a function of my data. It doesn't have any dependency on the parameter. And this right here I'm going to call g tx given theta in my case. So you can always perform this factorization. And we've seen that. So we had already done this proof several times when we were proving other things. So I will point out that in the factorization theorem, and they say this in the book, this doesn't have to be a distribution. And that doesn't have to be a distribution. But in our proof, we chose this to be distributions because it was easy to prove. So I can always factorize it using these distributions. I will point out, this is always going to be proportional to a distribution, even though it need not be a distribution, but it's going to be proportional to one. You can kind of see this over here. So I could have shuffled around the normalizing constants on everything and drug them over here. And so factorization is not unique. There's an infinite number of ways that you can do it. G doesn't have to be a distribution, but it's going to be proportional with distribution. So what's all the proportionality constant stuff? It's all the stuff over here. So that's just acting as a normalizing constant. Okay, so now the other part. And we get to learn a little bit more about transforming random variables. I love a good, obvious, easy proof. Stuff I can think about at 9 o'clock in the morning. Okay, so if factorization exists, we'll show that t of x is sufficient in our case. So if the factorization exists, then f of x given theta is going to be equal to hx g tx given theta. So we're going to invoke that factorization, and we'll show in just a moment that t is necessarily sufficient. So I'll just remind you. We'll show Tx is sufficient. And then we'll have both directions on this proof, and we'll be done. I want to point out that this is what I do when I'm trying to figure out what a sufficient statistic is. I'm figuring out what part of the data doesn't factorize away from the parameters. And that's all I'm doing. So I look at it, and I'm thinking about the factorization theorem, what part can't I get rid of? This is the conversation that Peter and I were having, where it's like, what do you think sum of the xi's minus x bar squared is sufficient for? It's sufficient for sigma squared because you couldn't untangle it from sigma squared. So go back to that example and you'll see that. And so what was Peter thinking about? The factorization theorem. He might not have called it that, but that's what he was doing in his head. Am I right? Yeah, sure, of course. He's going to agree with me no matter what. So anyway, we can go back and look at that example if you want. A reminder, I'll probably do that right after we do this. So what do we do to show that T of x is sufficient? We form a ratio and show that it doesn't depend on the parameter space. So this is going to look like fx given theta divided by ftx given theta. We want to show that this is a constant with respect to theta. So that's how we verify something as a sufficient statistic. So this is going to look like hx. So I'll invoke my if statement, gtx, given theta. So this is just this assumption right here. And we just used it in our proof. So if you don't use the assumptions that are leading to your conclusion in your mathematical proof, you didn't do the proof right. So you've got to use what's given. So this is our assumption. Here's the funny step in the book. So they're proving this in the discrete case. In the continuous case is very similar to this. We can do the continuous case if you'd like after we're done. So this is the discrete case. And I kind of like that they did the discrete case because I can do something very simple just to show you that this is true. But they're going to write this down. This is going to be sum over, I'm going to say y, I think that's the notation that they use in the book, given ty is equal to tx. And I'll tell you what this means in a second. I'll write that down. T of x. So this is my data set right here. T is my sufficient statistic. And this is going to look like f. Just write this down with some color. F y given theta. So this is my original distribution. So this distribution, this f and this f are exactly the same f's. This f and that f are not the same f's. Okay, so this is exactly the same f, is this one. I used to think that same stuff that Ankur was asking about, is that the same f? So why are we always using the exact same thing? Bless you. So I'll be clear, these f's are identical to each other. So maybe I'll make that one black so that they look even more similar, and I'll make this one purple so that they look a little different. Okay. So the question is what is this thing? So I want to take a moment to just kind of talk about it. What this says is these are the set of y's such that this condition is true. So let me just write that down. Set of y's that I can come up with such that ty is equal to t of x. So if we think about our binomial example that we started out with in this discussion, when we look at the sufficient statistics, so in the binomial example, that's the sum of the bits, the ones and zeros. So if I had an example where I have a vector of maybe 5 numbers, so n is 5, and let's say the sum of the ones and zeros is 3, I could end up looking at a lot of different sets, a lot of different vectors that have the same sufficient statistic. Let me say this with a little bit of math. N is equal to 5, just an example. So this is my binomial example. I'll say to Bernoulli. For me, it's all the same because I probably operate off of the binomial, but it doesn't matter which one you pick. So n is equal to 5, and let's say sum, so I'm going to have a vector of x1, x2, x3, x4, and x5. And I'll say this is I'll let this be x. Let's say this is a 1, this is a 0, this is a 1, this is a 1, this is a 0. So the sufficient statistic stat is sum of the xi's. I goes from 1 to 5, and this is equal to 3 in our case. So my set of y's I could have, oh, I made this too big, didn't I? There's 5, choose 3 of these. Well, what's 5, choose 3?
20.
20. So I don't want to write them all down. So I'm just going to write down some of them. 20 of these. We're not going to write them all down, but I could do this. 1, 1, 1, 0, 0. I could do a 1, 1, 1, 0, 0. So there could be a whole bunch of these. 0, 0, 1, 1, 1. So I can enumerate all of these different possibilities such that the number of ones in my vector of zeros and ones where n is 5, they just sum up to 3. So there's a lot of possibilities. Let's do another example. So let's do, oops, I'm getting rid of all my good stuff here. Just put that back. I made this one purple. I made this one red. just to think about what is this sum that we're writing down right here. So, dice example. Say x1, or I'll just call them d1 and d2. It's going to be an element of 1, 2, 3, 4, 5, and 6. I'll say di. It's an element of that. And these have width probabilities. One-sixth, 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 and one more one-sixth. 1, 2, 3, 4, 5, 6 of those. So typical dice experiment. I'm going to consider a transformation. So let's just say I is going to go from 1 to 2. So I'm going to have 2 dice. Two die are going to be thrown with these probabilities. So very basic stuff. This is probably how you learn transformation of variables in your very first probability class. So I want to consider this statistic, transform. I'm going to say the sum is equal to d1 plus d2. So this is just the sum of the two bases. So that's a transformation of variables problem. And you could do a lot of different things. You might use your convolution form to figure out what the sum is. However you work through your transformation of variables, it's fine by me. So usually when I'm summing things, I usually work through the convolution form or I derive it from scratch. So you need a bijection that you set up and then you have to integrate out one of the parameters, one of the things, so you have to marginalize it out. So I'd have to come up with S is equal to D1 plus D2, and then I'd probably have the difference between the two things. And I would come up with that joint distribution of the difference and the sum, and then I'd marginalize out the difference. So that turns out to be the same thing as the convolutional form. So, or we could do Stat 101 and figure this out from scratch. So let's say I want to know what's the probability and I'll make this the hardest one, just so we can enumerate everything. That S is equal to 7. Now you could figure out the distribution for S and work through it, or you could work through it like this, what they're writing down. So there's a whole bunch of different possibilities. So possibilities here. Are that D1, D2 are going to be equal to a 1 and a 6, or a 6 and a 1. Or I could have a 2 and a 5, or I could have a 5 and a 2. Or I could have a 3 and a 4, and a 4 and a 3. Any more? I could have a 4 and a 3, I've already got that one. I could have a 5 and a 2 now, I've already got that one. I could have a 6 and a 1, and I've already got that one. So there's 6 different ways that I can do this. And I can figure out what the probability of each one of these are. So these all have different probabilities. So this happens with probability 1/6 times 1/6 is equal to 1/36. And they all have that same probability. So the probability of that happening is 1/36. Probability that that happens is 1/36, 1/36, 1/36, 1/36, 1/36. There's 6 of those. And so I can write down what the probability of seeing a 7 is by adding all those together. So the probability that S is equal to 7 is going to be equal to 1/36 plus 1/36 plus 1/36 plus 1/36 plus 1/36 plus 1/36. 1, 2, 3, 4, 5, 6 is equal to 6/36. And my math is so bad I can't do this. You guys can figure out what the reduced form of that is. I'm being facetious, obviously. So pretty simple problem. So we can enumerate all of the probabilities from the original random variable. And so that's actually what we discuss in measure theory. If we started to talk about this is a random variable, what does it mean? That I can invert back to the original space that I'm operating on, and I can measure those elements in that original space, and then I can compute the probability of my transform. So that's what this is right here. So I'm going to look over all of the different collections of y's such that this constraint is true, such that the sufficient statistic is the same sufficient statistic. So that's what we're summing up. So this is just a transform. So I'll say this is a definition. Transformation. If I wanted to change this to the continuous case, all I have to do is change that symbol to an integral, and that's it. So you just integrate over the possibilities in a continuous space. You continually add them up. So it's your continuous add. I kind of like this, or at least this example, because we can enumerate everything. We wouldn't be able to do that if they were continuous. So that's all we're talking about right there. So that is a definition of transformations. Any questions about that? So not too elusive once you understand what the notation means. So now this proof is almost done. So h of x, g, tx, given theta, divided by sum, same indexing scheme. Understanding this proof is just an exercise in understanding what the notation is. And I'm going to substitute f because they're the exact same x right here. So I'm going to substitute in and use my assumption one more time. So this is going to look like h of y, g t of y, given theta. So this thing is varying in this sum, but this one's a constant because ty is always equal to tx. That constraint is always being adhered to. So this is a restricted space right here. So that thing's also t of x. Why? Because of that, the conditioning. So ty is equal to tx. So I'm going to look over all the different sets that I can form such that they add up to 7. So I didn't look at a 5 and a 3 because that broke my constraint. So this thing I can factorize out. Oops, not that thing. This thing I can factorize out. I'll just write it down. So the y's are varying, so the h has to live inside of the sum, but I can drag out this part that we're saying is the factor. So this is h of x, g t of x, given theta, divided by sum the y's given ty is equal to tx. hy, and now I'm going to factorize out this g right here. And I'm going to write it down as tx and not ty, even though they're exactly the same things, just because I can see the obvious cancellation. So this is equal to hx, sum of the hy's y given ty is equal to tx. So this is just a ratio of normalizing constants is what you end up with. So that's what this thing always is. When I formulate this conditional distribution, I'm always coming up with a ratio of normalizing constants that doesn't involve the parameter set. So it's equal to a constant with respect to theta. I'll just give this a little nickname just to remind you this is the ratio of normalizers. Voila, proof is constructed. And that's everything. So this is the tool that I use all the time. And then I just kind of mentally think about how to compress that statistic. And I think if I can go any further. So let's jump straight into minimal sufficiency. And I'll just show you an example, and then I'm going to run back in a little while, film a couple lectures for you. I'll put up all the lectures tonight. So we'll go into more depth on this, but I want to just look at a pretty basic example. Think about the Poisson model. So minimal sufficiency. And I find this to be a very powerful weapon when I'm doing computation. So it's not a theoretical interest, it's that I use less compute time and less storage if I can compress the dimensionality of the sufficient statistic. So I'll just say, the book says this. This is a function of all other sufficient stats. That's their definition. We'll look at that definition a little bit more. It's true, it doesn't help me to think about what the minimal sufficient statistic is, but basically, I can compute the minimal sufficient statistic from any other sufficient statistics. We'll look at some examples in the follow-up lectures. Here's an example. So let's say xi's are coming from a Poisson model. Usually I write lambda, but I'll just keep this as theta. So to match some of our notation over here, this means that I'll say I goes from 1 to n. So f of xi given theta is equal to e to the minus theta xi. Somebody help me out. What goes right here?
Theta to the xi.
Yeah. I know, the lambda thing is like automatic, isn't it? So, never used anything other than lambda for Poisson until this class. So theta is positive. Probably need to say that. Oh, and I forgot my factorial. And that always scares me when I see factorials. I figure, how am I going to compute that? And so the nice bit is that all the information about theta doesn't depend on the factorial. You never really need to compute it. At least if you're using likelihood functions. So the joint distribution, f of x, given theta, is going to be equal to the product. I'm assuming everything's IID. I haven't told you about the dependence, so there is none. Over xi factorial. And I can simplify that. This is going to be e to the minus theta n, theta to the sum of the xi's. I goes from 1 to n. And then I have this product down here. I goes from 1 to n, xi factorial. So all of my dependency on theta appears right here. This is going to control the asymptotics of everything. But our minimal sufficient statistic, our sufficient statistic is here. And I want to just point out that this is one-dimensional. It's a scalar. So one-dimensional. I'll also point out that if I wrote it out like that, the whole collection of xi's, x1 to xn, is also sufficient. They're both sufficient. But the whole collection is n-dimensional. So when I'm talking about the size of a sufficient stat, I'm talking about its dimensionality. And so which one would you rather have? Well, I would rather have the whole collection of data because I would want to verify whether or not this was Poisson. But if I did believe you that everything was Poisson and everything was IID, and I was ready to go to town in my computation, I would rather work with this because it's smaller. And I would just store that sum. So we don't need to know all the xi's, we just need to know this thing. We can already argue that this is the minimal size for inferring theta because theta is one-dimensional and the sufficient statistic is one-dimensional. You're not going to go any further down. And you could very easily convince yourself that's the minimal size of everything. This comment right here, a function of all other sufficient stats, I could have given you something like that, like this. So I could take this sufficient statistic right here, and I could compute a set that looks like this. So xi's, I goes from 1 to some number. I'm going to say k, which is smaller than n. And I could give you this. Some of the xi's, or I goes from k plus 1 out to n. So I could give you that thing as well. That's also sufficient. I could compute the total sum from it. And so I could compute the sum from this collection, or I could compute the total sum from these partial sums. And so this is where this definition comes from, a function of all other sufficient statistics, that I can compute this from any other sufficient statistic. And it will be of the minimal size. So I think when I first thought about that, that was a little bit mind-boggling to me, like what the heck kind of definition is that? So, but there is a more useful tool that we can use to verify everything, and I'll go into that in the next set of lectures that will be online, and you can watch those. But what I really do is I use the factorization theorem, then I use my mental capacity to think if I can shrink that down, can I simplify wherever that data is coming up. And so that's what I really do. And then if they ask me on a test, verify it, then I would use the formal tool that they present to you in the book that I'll present to you in the follow-up lecture. But the idea is that we want sufficient statistics that don't take up too much room. So, useful thing. Okay, that's it for now, you guys. So, enjoy the next couple days. I'm going to try to do the same. And Wednesday, when we come back, is St. Patrick's Day.
And it's spring break day.
And it's spring break, so we don't come back on that day. So I'll see you guys in the follow-up Friday in the midterm what we do then. Cool.
And the homework also. And the homework also.
And the homework as well. Yeah, that's right.
Will the midterm be posted on the website?
I'm going to send it to you guys, so I'm going to email it out to you.
Okay.
It's just easier that way.
Okay.
So I'm going to look at the current web list and send you a collection of problems, 6 or 7 problems probably. Normally, if it were in class, I'd give you 4 of those problems. So I'm going to give you a few more just for your practice. It's going to look and feel a lot like homework. So I'll probably ask you some verbal questions as well where you need to write down a sentence or two. And so try to throw it through a grammatical tool like regularly. So if you guys don't use those sort of tools, start using them. So, because I got to read this stuff at the end of the day. Okay, thanks a lot, you guys.
Thank you.